Okay, cardiac cycle. So events that occur during one heartbeat are all associated with what we call a cardiac cycle. So if you've ever taking your blood pressure or one of those machines at the grocery store or at the pharmacy, you've probably seen systole and diastole, or systolic rate, diastolic rate. So systole has to do with contraction of your heart muscle, and diastole has to do with relaxation of your heart muscle. Okay, so what are the three phases of your cardiac cycle? First phase is atrial systole, so that means your atria are contracting. Both of the atria are in systole, they're contracting. Both the ventricles are in diastole, they're relaxed. Okay, this is going to make the AV, or atrioventricular valves, open, but the semilunar valves are going to be closed. All right, in phase two, you have ventricular systole. Now the ventricles, both of them are in systole, they're both contracting. Now the atria are in diastole, they're relaxed. Which this contraction of the ventricles is going to open the semilunar valves, and it's going to close the AV valves. Now in phase three, you have atrial and ventricular diastole. So both atria and both ventricles are at rest, they're relaxing, they are in diastole. Now the AV valves are open, semilunar valves are closed, getting ready for another round of atrial systole. Okay. Those are the three phases: atrial systole, ventricular systole, atrial and ventricular diastole. Okay. Atria contract, ventricles contract, both atria and ventricles relax. Okay. So here's an illustration. Okay, phase one, atrial systole, lasts about 0.15 seconds. Okay, remember the atrioventricular valves are open, semilunar valves are closed. Ventricular systole lasts about 0.3 seconds. Okay, atrioventricular valves are closed, semilunar valves are open. And atrial and ventricular diastole lasts about 0.4 seconds. Okay. So atrioventricular valves are open again, semilunar valves are closed. All right, and remember we talked about the lubbed up sound. So when the atrioventricular valves close, okay, that's when you hear the lub. When the semilunar valves close, after the blood's been forced out, you get the dup. Okay. All right, so I'm gonna take a break and let you all explain to your partner the phases of the cardiac cycle. You can do this at home as well. Next concept we're gonna go over is cardiac output. So for cardiac output, it's basically just how much blood can you get out of your ventricle in 1 minute. So, output is volume of blood pumped out. And the average cardiac output is 5,250 milliliters per minute, or 5.25 liters per minute. So what affects your cardiac output? Well, how fast your heart's beating, or how many beats you get in a minute, and how much blood can be pumped out each time your ventricle contracts. That should make sense, right? Volume times speed. So heart rates measured in beats per minute can be adjusted by your autonomic nervous system. Also, temperature can affect your heart rate. All right, so proper electrolytes are needed to keep your heart rate regular. So that's another reason to make sure you're getting your electrolytes. Stroke volume, that's just how much blood your ventricles can pump each time there's a contraction. Stroke volume is affected by how strong the contractions are. The stronger the contraction, the higher the stroke volume. Okay, it's influenced, again, by electrolytes concentration in the blood, as well as your autonomic nervous system. So other things that can affect the strength of your contractions in your ventricles would be venous return. So how much blood is getting back to the heart through your veins, as well as differences in blood pressure, okay? So your blood pressure can impact how strong the contractions are as well. Okay, so this is an image linking your nervous system and your cardiovascular system. So how do you regulate heart rate, or how does your body regulate heart rate? Well, your baroreceptors in the aortic arch, okay, part of your aorta, as well as your carotid arteries, okay, branch off the aorta, can monitor your blood pressure. Baro has to do with pressure, like barometric pressure. You also have nerve signals, and they're going to be sending a signal from those baroreceptors to the cardioregulatory system, center in your nervous system. So then you're going to get increased parasympathetic signals that can tell you to decrease your heart rate via the vagus nerve. So if you get vagus nerve stimulation, it can make someone's blood pressure drop a lot. But if you have increased sympathetic signals, it's going to make your heart rate increase. Okay, so parasympathetic stimulation makes your heart rate decrease. Sympathetic stimulation makes your heart rate increase. Just think about it. Your sympathetics, your fight or flight. Okay, hope you remember that. Fight or flight, you're going to need a lot of blood flow. That blood pressure, the heart rate's going to have to be higher. Okay? Now, what about blood pressure? So if you have increased sympathetic signals, makes your blood pressure or blood vessels constrict. Okay? And that, by constricting the blood vessels, pressure is higher. All right, like if you press on the end of a water hose, right? Water comes out with higher pressure because you've constricted the amount of space the water has to come out. All right. So we talked a lot about the heart. All right, so let's talk a lot now about blood vessels. So what do they do? What do your blood vessels do? Well, help you move blood as well as what's in the blood. Blood vessels help you exchange gases, right? Oxygen, carbon dioxide. Blood vessels help you regulate blood pressure. Okay. They also control the direction of blood flow. Okay. Because they are a pathway that blood has to go through. Now, some of the blood vessels that we'll study are arteries and arterioles. Okay. Arteries and arterioles, but just think about the A in arterioles and arteries, they transport blood away from the heart. Arteries away. And arteries and arterioles have thick and strong walls. And they are composed of layers or tunics. The inner layer, the endothelium, okay, it's basically like heart epithelial cells. It's called the tunica interna. It's internal. Now you also have an outer connective tissue layer, tunica externa. It's the outer layer. And in the middle, you have a layer of smooth muscle and elastic fibers. Because it's in the middle, we call it tunica media. And we don't really use tunics much these days, but tunic is basically like a covering. Okay? People used to wear tunics. Okay. So the elasticity in your arteries and arterioles means they can stretch and recoil back to the original size or shape. Let that artery expand and recoil. So we know what arteries are in general, but what are arterioles? Well, they are small arteries. Okay? So arteries generally flow into arterioles. It's because they're smaller, sometimes there's more constriction relative to an artery, but generally speaking, they can be constricted or dilated as well. And constriction or dilation of those arterioles will affect how your blood's distributed in your body as well as the blood pressure. So depending on what your autonomic nervous system is doing, that will determine how many arterioles are going to be in a contracted state. Okay. All right, so we talked about arteries, we talked about arterioles. What about capillaries? So these are blood vessels that are so small they are microscopic. And they're composed of just one layer of endothelial cells. And they are where the action happens. They are where gas exchange and nutrient exchange happen. Okay. So if your blood is carrying essentially nutrients from your food you ate to the tissues, capillaries are where it's exchanged with the tissue. Okay, if your blood has oxygen, where capillaries are where the oxygen is distributed to the tissue, and where that tissue is picking up carbon dioxide. Okay. Or the tissue is providing carbon dioxide, rather. Now, capillary beds are not just all being used all at the same time. Okay, most are going to have what we call a shunt, which allows you to kind of shut them off or not use them. And so to control how much or whether or not blood's going to flow into the capillaries, some of them have what we call precapillary sphincters. Okay, so they constrict. It's essentially at the proximal end of the capillary bed, so blood can't really get into the capillary bed. So exchange will happen across the thin walls of the capillary. Right. The good news for your body cells is most of them are close to some capillary. So they're close to some opportunity for exchange. So generally, oxygen and nutrients will leave a capillary. Exception to that would be the lungs, where capillaries are going to pick up oxygen. But generally speaking, cellular wastes are going to enter a capillary, okay, so that they can be disposed of. Okay, so they got to pick them up from the tissue to get rid of them. Okay. So your capillaries are, or your bloodstream is kind of like the equivalent of both the Amazon or UPS delivery person and the garbage pickup. They were the same company. Okay, so think about it that way. All right, so here's an illustration, shows you an arteriole and a venule. And we haven't really covered that yet, but venules are small veins. And in the middle, we have a capillary. So the end of the capillary closest to the arteriole is called the arterial end. And there, you have blood pressure that's higher than the osmotic pressure. And osmotic has to do with just the difference in concentration of water on either side of that membrane. There, and because the blood pressure inside the capillary is higher than the osmotic pressure, it's going to force pressure out, net pressure out. Now, at the other end, closest to the venule, we call it the venous end. And there, the osmotic pressure is higher than the blood pressure. Okay? So then you're going to have net pressure going in. Okay. So what we see here is that at the arterial end, you have water leaving, okay, oxygen leaving, amino acids leaving. Okay, so you're distributing your nutrients. Because remember, you have a higher concentration of oxygen in the capillary than you do at the tissue. So that's how you get oxygen to your tissue. Okay, remember diffusion? All right. Same for your nutrients, your amino acids, and your glucose. Typically, because your tissues have already used up their oxygen that they had previously, they have a high concentration of carbon dioxide. So that carbon dioxide will go into the capillary as well as waste products. Okay, because again, they've been building up waste. All right, and toward the venous end, now water starts coming back in to the capillary. All right. So what affects what affects exchange of materials through the capillary? Well, I'm glad you asked. Well, you have three things. One is blood pressure, one is diffusion, one's osmotic pressure. So the force of blood being pushed through the capillary can affect how well materials get exchanged across the capillary. Okay, the concentration gradient, depending on what's the difference between the inside of the inside of the capillary and the outside of the capillary. Osmotic pressure. So if you have a difference in solute concentration on either side of the membrane, you can get osmotic pressure. Okay. Okay, we just kind of went over this. At the arterial end of the capillary, you have a higher blood pressure than osmotic pressure. Water and small molecules get pushed out. At the venous end of the capillary, lower blood pressure, same osmotic pressure. Water, waste start diffusing into the capillary there. At the midsection of the capillary, cells can use oxygen and glucose for cellular respiration. Remember, that's how we make ATP. Okay. Cells get to use the amino acids for making proteins, right? Remember amino acids, the building blocks of proteins, biomolecules, okay? Tissues are gonna release their carbon dioxide and waste products that they make as a result of metabolism, cellular respiration. And they're gonna go into the capillary through diffusion. A difference in concentration. All right, so here's another view. Okay, so here's microscope view. Want to make sure you know the walls of the arteries or arterioles are going to be thicker than the walls of the veins or venules. More smooth muscle, okay? A thicker layer of smooth muscle. So the veins can sometimes be bigger, but they have less. They'll have basically fewer layers of smooth muscle. All right, and just to review, here are layers. Here's our tunica intima. All right, tunica media, tunica externa. Okay. All right, so here's your artery, your arteriole. Here's precapillary sphincter, control whether or not blood's going to go into the capillary bed. Okay, you get diffusion here. Whatever's left, it's going to go into the venule and then the vein. All right, here's another view of capillary bed. All right, so we've covered arteries and arterioles. Let's let you take a minute, talk with your partner about what you've learned about arteries and arterioles. You can do this at home as well. So now that we've covered the arteries and arterioles, let's spend some time on the veins and venules. So just like arteries and arterioles move blood away from the heart, veins and venules move blood or return blood back to the heart. Okay. So venules are small veins. They're going to drain blood from the capillaries. And they come together, multiple venules come together to form veins. Okay, vein walls are going to be thinner than what you'll see with arterial walls. Less smooth muscle. Your veins actually have valves in them like you do in your heart. And what do valves do? They prevent backward flow of blood. And that should make sense because we just said that your veins don't have as much muscle tissue, right, as arteries and arterioles. So if you didn't, and you don't really have the amount of force to move blood back to the heart, all that blood would just pool in the bottom of your body. Okay, so as your body at least gets to a certain point, you get basically checkpoints where you don't have to go all the way back down to the bottom. It's kind of like, I guess, getting to certain levels on a game where if you get to this level, you don't have to start all the way back at the beginning. You can start, partway through. So, all right. So some medical conditions related to this, varicose veins, right? People especially if you're concerned about your appearance. People don't like varicose veins. And what these are irregular swelling or dilations in superficial veins. When we say superficial, what does that mean? Not that you're thinking you're special. You know, people say, "Oh, that person's superficial."
On the outside.
It's closer to the outside. Thank you.
Like those in your vein like pop out. So you can see them like in the neck and arms.
Yeah, a lot of people see them in the legs. That's where a lot of people see varicose veins.
Yeah.
Arms, legs.
In your legs.
Yeah. So, now hemorrhoids, okay. Now this is anatomy class, so we can talk about things like this, right? But hemorrhoids are actually varicose veins in the rectum, okay? So obviously that's a very, painful place to have varicose veins, right? So varicose veins can develop when valves in your veins get weak, okay? So if the valves get weak, you're gonna get extra pooling than you should, okay? Or you'll get too much blood flow to certain spaces and your veins aren't able to accommodate it, or too little. But they'll essentially pool in a certain place, so you get too much and your vein swells. All right, phlebitis. Remember, anytime you see itis, it means inflammation. So this is inflammation in a vein. So if you think of an phleb is a root word for vein. So anybody know a phlebotomist? All right. So where do phlebotomists typically get blood from a person? In the veins, right? So that's why they're called that. Okay. So one of the consequences of inflammation in a vein is that you can develop a thromboembolism. Okay, I think we discussed that previously. So if you get basically a clot that moves and ends up blocking blood flow in a certain area, and as we know, that's not a good thing, right? Okay, another aspect to blood flow is velocity. So there is a whole, area of science where they take concepts in physics and concepts in biology and they merge them, okay? Because you might say, well, what are we doing talking about velocity in anatomy class? Well, blood can move at a certain rate of speed, okay? So blood flow is going to be slowest in the capillaries, okay? And that should make sense. Why? Why would it be slow there? Because there's very small area to get through, right? So where would blood flow be the fastest? In the arteries, partly due to the size and partly due to the force of contraction, right? So, and one of the consequences to that is you really want it to be slow because you're wanting time for gas exchange and for nutrient exchange, right? If it was moving too fast, you wouldn't be able to get everything on, from your blood. I mean, it's kind of like if you were trying to get stuff, let's just say you're trying to get things for your family and it's on a conveyor belt. Are you going to be able to get more stuff and put it in your cart if the conveyor belt's moving fast or moving slow? Slow, right? So that's basically how it works. All right, blood flow is going to increase as the venules combine to form veins, okay? Because you're getting into larger and larger spaces, you get more blood flow, okay? But the velocity or the speed and direction of blood that's returning to the heart is low if you compare it to blood leaving the heart. Why? Well, again, typically not much smooth muscle squeezing that blood through your body in veins. Also, some of those veins are moving against gravity, right? You move blood from the lower portion of your body up. Okay, so this chart or graph shows you total cross-sectional area or cross-sectional area of your different blood vessels. Also looks at velocity. Okay, so your large arteries and your aorta are going to have most of your velocity. Okay, and it's going to drop off. The velocity is going to drop off as you move toward small arteries, arterioles, capillaries. Okay, now, and so that's what you see here. Velocity is dropping off, but as you move into venules, small veins, large veins, and the vena cava, your velocity starts to increase. Now, if we look at the graph here for total cross-sectional area, you have low cross-sectional area at the arteries and the aorta, but high cross-sectional area at the capillaries. And so that might not make sense at first, but essentially what we're talking about is area where blood is touching the endothelial surface or able to get across. In a big artery, most of that blood is sort of in the middle. But in a capillary, it's almost like single file line, right? So all those blood vessels are all those blood cells, the nutrients, the oxygen. There's a large amount of endothelial surface that they are touching, okay? So it's, big circle versus small circle. All right. Talked about blood flow. Let's talk a little about blood pressure. So blood pressure has to do with force of blood moving against the walls of your blood vessel. Okay, so when you get your blood pressure taken, that's what it's actually measuring. How hard that blood is hitting against the walls of your blood vessels. Now, should make sense to you that your blood pressure is going to be the highest at the aorta, okay, because that's where you've got full pressure of the left ventricle forcing blood out, plus you have smooth muscle in the wall of the aorta. And it's going to decrease as you move away from the left ventricle. Okay, it's going to be lowest at the vena cava. Now, your blood pressure will fluctuate between your systolic pressure and your diastolic pressure, right? Your contracting blood pressure, relaxing blood pressure. Now, your what we call mean arterial blood pressure. Okay, if you've worked in hospitals and they do, or clinics when they're doing blood tests, you may have seen this term. So it's an average over time of your pressure across your arterial network. Okay. And how you calculate it is you multiply cardiac output, okay, how much or a volume of blood that's being pumped out in a minute, times what we call peripheral resistance. And peripheral resistance just means the resistance to blood flow between the blood and the walls of that blood vessel. Okay. So how much resistance is there to blood flow? So if you increase the cardiac output, you'll increase the mean arterial blood pressure. If you increase the resistance, you're also increasing the blood pressure, right? More resistance, more pressure. Right? So this shows you change in pressure, blood pressure, as you go away from the left ventricle. Again, highest at the aorta, lowest at the vena cava. You get a gap here in the arteries between systolic and diastolic, but that basically goes away in the veins because, again, you don't have much smooth muscle to be contracting, okay, in the veins. So how's blood pressure related to cardiac output? Well, faster your heart is beating, more cardiac output you have. It should make sense. More beats, more squeezing, so you get more blood being moved. Increase the cardiac output, that's also going to increase your blood pressure. More or higher your stroke volume is, higher your blood pressure is going to be. Now, your stroke volume and your heart rate will only increase your blood pressure when you have adequate venous return. Okay. So if you don't have enough blood coming back to the heart, your overall blood pressure doesn't change that much. Okay. Now, what does venous return depend on? So what affects how much blood can come back to the heart? Well, if you have a difference in blood pressure, it's going to affect how much blood comes back to the heart. Also, what we call the skeletal muscle pump, as well as the respiratory pump. So remember I said that the veins don't have a lot of smooth muscle? So if the skeletal muscles around those veins contract, it's going to compress or press against the walls of those veins. Okay, and that causes blood to move through that vein, moving past the valves in the vein. Okay. Now, during inhalation, when you're inhaling, your thoracic pressure actually falls and your abdominal pressure starts to rise. And you start getting blood flow from an area of high pressure to area of low pressure. Okay. So that will also affect venous return. Now, also your total blood volume, how much blood you have in your body, will affect venous return. So if you have less blood, if your blood volume decreases, that's going to cause your blood pressure to fall because there's essentially less blood hitting the walls of your blood vessels. But if you increase your blood volume, your blood pressure is going to go up because now you have more blood hitting against the walls of your blood vessels. Okay. So here's an example. The skeletal muscle pushing against a vein. Okay, it's squeezing that vein, it's pushing blood so it can move past the valves. And when the valves are closed, it prevents blood flow from moving back away from the heart. So blood only gets to go toward the heart in the vein. Okay, so let's take a break here and talk about what you've learned about veins and venous return, cardiac output, blood pressure. Okay, so let's hear some discussion on that and what you picked up there. Anybody in here graduating this semester? Okay. Well, congratulations. Just wanted to remind you, if you want to have a photo in the virtual ceremony, last day to take that photo is October 27th from noon to 2 p.m. in the Francis Ross Ballroom at the Student Center. So just wanted you to be aware of that.
They contacted you? What was it? What? They contacted you? They contacted you? They never contacted me either. No, I won't go there yet.
No, sis, you're wasting your time.
No.
But, I mean, if you
Fourth
want to
is
do it,
our
do it, but I wasn't wasting your time. That program's a joke.
Horses are against you.
I'm gonna correct myself. If I pass A and then I'll be graduating. When I pass.
Should we get it on Miss Hanson or Miss Parker?
You can email it back.
Are you gonna do that? I mean, the virtual picture?
Just put my name on a piece of paper like I did last year.
Hand it over.
And send it to me. I'll probably have to work.
We can't graduate till we take our test.
No, when we pass A and P, we graduate, they won't give us our certificate till we pass our test. Instead of my girl.
Mm-hmm.
Right here, the total cross-sectional area
Mhm.
is basically where the veins and the arteries are coming up and just connected to the capillaries.
Yeah, the capillaries are in the middle, yes.
Right,
But essentially it's,
they're just crossing over.
well, it's basically artery, arterial, capillary, venule, and vein. And so it's just that's sort of the direction of blood flow. The sectional, cross-sectional area that has to do with essentially what percentage of the blood is actually touching the walls of the blood vessel.
Okay, okay.
Because like an artery, it's just kind of like the big container, and most of it's in the middle. Whereas a capillary, it's so small, all that blood is basically getting to touch the wall of the capillary. That's how you get more exchange.
Oh. That's right.
I'm figuring the blue right now.
911.
A little more about peripheral resistance and blood pressure. Peripheral resistance, again, how much pressure or against the resistance to blood flow there is, can be regulated by the nervous system. So you have a vasomotor center in your brain, and it regulates what we call vasoconstriction. Vaso just means vessel. And it can cause blood to be moved or shunted so that it goes to another part of the body. Peripheral resistance can also be regulated by the endocrine system through hormones. So epinephrine, norepinephrine, that can increase your heart rate, constricts your arterioles. You also have the renin-angiotensin-aldosterone system, where angiotensin 2 can constrict arterioles. Aldosterone can cause your kidneys to reabsorb sodium in water. Antidiuretic hormone causes your kidneys to reabsorb water and to vasoconstrict the blood vessels. Atrial natriuretic hormone, okay, it's going to inhibit renin, okay, as well as aldosterone secretion. So it prevents them from being secreted. Okay, so real quickly, show you here. Again, you've got your posterior pituitary, kidneys, and the heart. So if you've got low blood pressure, high blood electrolyte concentration, your posterior pituitary is going to release or secrete antidiuretic hormone, cause you to reabsorb sodium, reabsorb water. Consequently, your blood volume rises. So you get to a normal blood pressure and volume. If you have low blood sodium level and low blood volume, kidneys are going to secrete renin and angiotensin 1 and 2. Okay, and that's going to lead to production of aldosterone. All right, now will also cause you to reabsorb water and sodium so you get a normal blood volume, blood pressure. If your blood pressure is too high, your heart releases the atrial natriuretic hormone. So you start releasing or excreting sodium and water, so you lower your blood volume till you get to normal blood pressure and volume. All right, so we will start talking about more of the circulation next Monday. Okay, so we'll try to finish up the chapter on Monday. So you can go ahead and work on your exit tickets, and that'll conclude our discussion of the circulatory system for today.